I would like to shift gear just a little bit, and I've kind of cheated a little here. I sent in a title that said Design of a Full-Page Tactile Array, and actually what I'm going to talk about is Co-Design of a Full-Page Tactile Array. And the reason I want to do this is because this is the journey that we've been on with the microfluidic device we're working on, which is still on its journey. But I thought it would still be interesting to talk about the process, just to talk about the implications as I've observed them as the co-designee, and learned a lot along the way myself. I couldn't have predicted some of the things that are going to be important if we're going to think about co-designing in devices with particular user populations. So co-design is a commitment to work from the very beginning of a project, from the ground up, with people from the end user community embedded in the design process. And by embedded, I mean they really do need to be partners from the very beginning. That's the principle of co-design, and it's something that's becoming more pervasive in human-computer interaction as we move beyond what was called third wave HCI. Third wave HCI, with the idea being that we need to be able to represent in our design, in our work, in every aspect of what we do, the multiple perspectives of all the people who are likely to come into contact with the things that we're making. So what does this mean for a community of blind users, which would be the target community in this case? So obviously, if you're hoping to design a device for blind users and you really are committed to co-design, you're going to have to think about accessibility of all stages of your process. So this means accessible tools for collaborative writing, even at the stage where you're trying to put the grants together. Accessible tools and methods for prototyping, which can be very challenging, and that means both hardware and software prototyping. Accessible tools for running focus groups, so that means your blind PI or co-PI needs to be able to help develop materials for your focus groups as well, so that they need to be involved in the process of designing those things too. Obviously, and then in running and running, focus or studies themselves, and in gathering data, analyzing the data, and finally in presenting the results. And some of these you'll get for free. So things like PowerPoint is moderately accessible as I present some of the findings from our current work, but some of them are more challenging, like really good ways of physical prototyping are still quite hard, although they're getting easier. But if you commit to a fully accessible process of co-design, you get a lot for free. For a start, your project's going to be rooted in a lifetime of experience for at least one member of your team. And that might help you avoid making some quite naive mistakes, which, anybody who's not rooted in a community of use could possibly make. And to avoid making them it takes quite a lot of effort. The other huge benefit is that one of your project team members is going to be really embedded in the wider user community and is going to already hopefully have a lot of their trust. As a member of a community to whom people often come with designs, you are very skeptical of people who don't have deep connection or deep experience in the community, because it tends to be a process by which they're sort of telling you that they've got a technology which is going to solve one, if not all, of your problems. And you're sort of sitting there going, how many times have I seen this before? Because though it might be a first for them to bring it to your community, it's very seldom a first for the community to see somebody even trying to present a solution to a particular problem. And I'm not going to say we were any different, even though I'm visually impaired myself. We also received some pushback when we brought some of our ideas to our potentially end user community, and are likely to do so in the continuing development of the devices that we're working on. But the other important thing is that if you are able to do this, your design process is going to really reflect the needs and requirements of the community. In this case, very much a touch-first approach to design. So I'm going to go quickly over this because I'm not intending to brag here, but what I wanted to show was that, if you have somebody on your team, all of these things might become available to you for free. In my case, I have experience reading and writing Braille. I've experience in using other codes like music and math. I've also created and used my own tactile diagrams. I also happen to come for free with some experience in designing haptic interfaces and also a background in HCI. And the important thing is I'm not the only person like this. There are lots and lots of blind people out there who have this kind of experience, and you want to grab them quick because Apple and Google and Facebook and Microsoft is beating you to it and is stealing all the best designers. So if you want them in your PhD research and on your grants, you need to be a bit more proactive. So that's sort of to talk about being a little bit embedded in the community, but let's think a little bit about naive mistakes. So here's one that we were presented with when we said we wanted to design a full-page tactile display. We could have made almost twice as much if we'd gotten a couple of dollars for every time somebody came up and said, well, why don't you just make a single cell display? Because that's cheap. You only need one cell. After all, you know, the fingers, or maybe two cells, because you got two fingers and they only really ever touch two Braille cells at a time, which is true for the focal awareness of Braille reading. Yes, two fingers are sufficient. I'm just going to, yeah, I'll show this if anybody asks. But yes, if you've seen some of the videos that I've shown before of people reading Braille on a surface that has been recorded from below, you'll see that definitely there are only two fingers in focal contact with the Braille, but there are other fingers gathering other information along the way and helping to keep the hand in a straight line and all these other parts of reading. So we decided we needed to become Mythbusters in this case, and we ran a study to look at the question of how much display is enough. So we could have single cell displays, which would mean that there was literally only one cell under one finger or perhaps each forefinger. We could have a single line display, which is what we have now, or we could have a full page display. And the first thing we looked at was the contribution. We had a hunch that, and maybe one of the reasons why blind people find it so hard to read single cell displays and have sort of moved away from purchasing devices that are based on that sort of paradigm, is that it's very hard to have some slip between the finger and the surface. And if there's one thing you probably remember from the work of people like David Katz, is he said that if there's no movement between the finger and the surface, then the tactile image basically fades from the tactile view. So we figured that maybe slip was involved, and maybe proprioceptive feedback, so moving our hand across the sheet of Braille. Maybe that was somehow important in guiding your actions in the sort of Gibsonian sense of being able to pick up information using active touch. So here was our claim, that we claim that the reason why single cell displays might not be successful is that there's probably a role for both proprioceptive feedback, so the movement of the arm, and also slip or a sliding contact between the finger and the Braille surface. So we tried to quantify the relative contribution of these two things. So we had this quite elaborate set of apparatus. We had what we call the mouse, which was basically like a traditional mouse with a Braille cell on the top, where you have proprioceptive feedback, but the Braille just pops underneath the finger, so your finger is not sliding across the Braille. The Braille is changing because your arm is moving and the text on the top of the mouse is being refreshed. The other condition here was what we called a clock condition, because a lot of early digital Braille clocks were like this. You literally just put your finger down and the time changed underneath your finger. And then these were the other two, what we call line and tape. So line was just a traditional refreshable Braille display line. So you moved your finger and the text didn't move. And the tape condition was where you had the sliding contact. So the line of Braille moved onto your finger, but you had no proprioceptive feedback. So we had these four things. It was crossed like the clock condition had neither slip nor proprioceptive feedback. The mouse condition had proprioceptive but no slip. The tape condition had, it had slip but no it had slip but no proprioceptive feedback, and the Braille line had both. So here was what we discovered. This is our myth-busting exercise, remember? So what we discovered is that both of the conditions where the braille slid past the finger, so where you were either moving your hand or the line of braille was sliding under your finger, people were more accurate in reading the characters that we presented. We presented random characters and they had to just read them. And they were much more accurate when there was a sliding contact than when there was no contact. Proprioceptive feedback had a little effect, but not much. So the sliding contact turned out to be the most important thing. So again, just to go back to the idea that that could have been a naive mistake, and has been a naive mistake that has been made in so many cases. And if we could get all the grant money back that has been spent on devices that use the sort of mouse paradigm, or even just a single cell refreshable paradigm, and sort of reuse it, it would be so great. And it is frustrating to see people still coming up with those ideas. And it's just a question of sort of asking somebody who might know to tell you, is this a good idea or not? So going back again to this idea of having a project team member deeply embedded in the community, it's not just that team member will have access to lots of participants, because that's sometimes what people think having an embedded team member might be, but they also have access to the culture of the community. In this case, it's the culture of braille reading and access to braille. And it's complicated because it has to do with, whether school children had access to reading braille, whether they were allowed to have their tests made in braille. If the school district or state invested in braille teaching, then the person got to learn through braille. And if the school or state didn't, then that was something that wasn't available to them. And one can say that, well, it's you don't need braille anymore because you can use speech, and that's true. A lot of the time I do use speech, but I was fortunate enough to come up through a system where I learned braille, and so I have basic literacy, independent literacy that's based on being able to interact directly with the text of the books or whatever that I'm reading. So there's also a cultural aspect, and people in the deaf community will tell you too that there are subcultures within the deaf community of people who have grown up signing, which is a language in its own right, versus people who have grown up lip reading, and those have very different implications. So things like that are what you get for free if you're able to have somebody in your research team from the beginning who understands the nuances of these kinds of things and the pros and cons of making certain design decisions along the way. And this is also important in co-design. Your design process reflects the priorities of the end user community at every stage. And this is what I mean here, which is this idea of a touch-first approach to design. And this is kind of the point where I sort of transition from the what we know to what we don't know yet, because the next set of slides have to do with thinking about the issues that come into focus when you start moving from a single line of braille to a full page of braille. So here's the first thing that happens. As the size of a tactile display increases from one line to one page, the challenge of orienting oneself on that page also increases. So where you might once have been able to sort of find the cursor or bring the cursor to you on a line, now this is scaled up to a whole page of dots. So from 8 times 32 dots for a fairly standard braille display to 8 times 32 times 26 dots. That's the searchable area, effectively. And so the strategies that might have worked for a single line display may no longer work for a full display, and in fact probably won't. So the kinds of things that now come into view are, how do you stay oriented if you're moving between pages of a text or different views of an image, we'll say, or a graph, or zooming in and out of things. And this work here has, people like Pressure here have looked at this and have some initial findings that are point us at least in the right direction to start looking. So here's the first thing to think about, the idea of context and focus. So when you're using a touch screen or a mouse, as a person with vision, you're able to see the context of what you're doing. You can see the whole page of the document or whatever, and you bring the cursor to where it's needed. With Braille, on the other hand, when you put your finger down on the display, you have focal awareness, and you have to search and build up the image by moving outwards from the point of focus. So there, the strategy that might be more effective would be bringing the cursor to where you are, rather than going and fetching it and calling it to where, summoning it to where you are, I suppose, as opposed to picking it up and bringing it with you. And this whole process is called cursor routing, and it's been familiar for single line displays because it's how they work too. You're looking at a character, or you might want to edit something, and you just press a button below the current cell you're reading, and the cursor comes shuttling over to where you are. And so expanding that then to work for a full page tactile display could be one way of solving the problem. So as I just sort of inferred, the issue here is that with vision, you have context first, and then you focus in. With Braille or tactile documents, you have focal awareness first, and then you have to build up context. And these both imply very different strategies of interaction. So that the outcome of this then is, if you're trying to attract somebody's attention, you can't just sort of like flash one dot in the middle of the tactile array and hope they notice it, because their hand might not be there. So you have to find other ways of attracting attention. And these might include, you could have blinking dots, which actually sometimes you can hear, or you could have some kind of global effect that says, hey, you need to pay attention now. And you can also use things like, on some displays, you can use dot height. So some displays will have the ability to make higher or lower dots, and you can literally highlight something by doing that. Or you can have a grid which sort of comes into being in order to guide you to the point where your attention needs to go. Or there could be completely other things that we haven't looked at yet. So this idea of overlays, some kind of overlay that guides you. But it's clear that one approach might not work for all contexts. So for interacting with static content like text or even a tactile graphic, one thing might work. But when it comes to interacting with dynamic content, even creating and editing text, especially in a collaborative situation where something can change at a point on the display that you're not currently touching, then there might need to be other strategies. The same is true for creating and editing graphics, or even going beyond that to creating and editing sound, for instance, audio sound waves, which is the world that I came from. And you could have tactile animation or any other kind of interactive media. But the benefit of a full-page tactile display is that you have, while there are more challenges, there are definitely more things you're going to be able to do. You can work with Braille codes that are non-textual, in other words, codes like music that stretch over a couple of lines, or mathematics is another code that does the same. You can have collaborative editing, which is something that is really causing a lot of challenges for visually impaired people at the moment, because the screen readers that we use, which are the speech-based systems, work on a model where the screen reader follows whatever has focus, but if two people are working on a document, the focus is not going to stay in the same place, and so the screen reader just literally can't cope. So another thing that is a huge benefit, and probably one of the greatest benefits of these devices, is the ability to create and edit spatially organized information. So we have static tactile images that we use for maps and graphs and charts and things, but being able to have refreshable versions of those images that one could interact with in real time or edit oneself. So you could label your own graphics, which is something that we've never really been able to do. creating and editing graphics. All of these things are going to revolutionize the way blind children can learn in the classroom, and students can learn at college. So can you imagine, for instance, having gone through your whole school career with never being able to label a graphic yourself? So that's the kind of thing we want to address. This piece of work that's cited here is some work I recently did with my student Rishi, where we had people basically complete a crossword puzzle. And what we were looking at here was how to distribute information across modalities. And our hunch is that we might be able to offload much of the spatial information in a task like completing a crossword to a full-page tactile array to ease the burden of the blind person and having to remember where everything is. But it's still possible that we'll need speech output because tactile displays have quite limited real estate and Braille takes up quite a lot of space relative to printed letters. So we might end up with a hybrid format where one could touch part of the display and have it speak its contents. And that's in fact what we did here, because the display we were using was not good enough resolution to actually display Braille characters, but we could have a dot per character of the crossword. So we showed the layout of the crossword and allowed people to find things and press on them to have them read and fill in parts of the crossword. And what we discovered was, we compared this with a traditional on-screen version of the same crossword. And what we discovered was that where people had access to the spatial layout, they had a much better mental representation of what the crossword was like and how all the pieces fitted together. The screen reader users didn't really interact with the crossword in its spatial representation at all. They just bypassed that completely and just answered the clues in a list, which kind of, it removes part of the kind of compelling thing about a crossword, which is trying to fit all these words together in a grid. So they were able to complete the task. The argument is that the task they completed wasn't the task of completing a crossword. It was more like answering a set of questions in a quiz. So, and you can find this paper, it was in CHI 2020. So another huge benefit that is going to arise from these displays is that we're going to be able to distribute tactile images on demand. At the moment, the process of creating tactile images is very cumbersome. Teachers can do them themselves by using kind of collage-based techniques and then either giving the raw collage to the student or having it copied using plastic vacuuming techniques. But then if the student needs something more complex that needs to be created by a more skilled transcriber, you have to kind of build in the lead time to have the book with the diagrams or whatever prepared by the transcribers and then shipped to the student. And these volumes are typically very bulky, so for the student to carry them around, in addition to all the other things they're carrying, it's also very demanding on them. So if you can create and edit and distribute tactile images within the text that they belong to in an electronic form, again, it's going to really revolutionize the way that blind children can work in the classroom, even to the point where a teacher could have a teaching assistant create a tactile version of a graphic in real time and share it with the student. The image here is of the Hyperbraille, which was a full-page tactile display that I think some of you might have seen. It's been at Haptics and the Haptics Symposium quite a lot. But this is the kind of full-page array. Another thing that's going to be really great is to have, as I mentioned, blind students create and draw their own images. And this was a nice piece of work done on tactile drawing by Watanob and colleagues, where they showed that even allowing blind children to be able to recreate things that they were trying to understand the form of improved their ability to learn spatial concepts and relational concepts in a way that just passively acquiring this information from a tactile diagram did not. So to summarize then, the transition from a single line display to a full page display requires a complete reimagining of what interaction with these devices might be. So for instance, tactile interaction equaling focus before context means that you're going to have to think about what happens when you've got larger displays with more items to be searched. or how you're going to manage attracting attention. Different tasks and contexts are going to require different strategies. But the important thing is that the advent of these large-scale tactile arrays is as significant for blind people. The transition to this kind of format is going to be as significant for blind people as the transition from the command line to the GUI was for sighted people. And as with the transition to the graphical user interface, it's going to require us to come up with completely new forms of tactile interaction for these displays. And the argument here is that this can only succeed if these displays and the content that goes with them is designed from the bottom up with the complete collaboration of the end user community for whom it's going to make a huge difference in their lives. And if they have input, you're going to get much more benefit at the end of the day from the design of the tactile displays. So just to acknowledge the people, all the people involved, Alex Rosamano, Brent Gillespie, and myself have spun out a little company to make our own microfluidic display. Val Morris, who passed away in 2017, was very involved in some of the early work that we did at Smith Kettlewell. And my student Rishikesh Rao, whose work you saw there with respect to the crossword puzzle study. And a whole bunch of support from organizations and federal grants. So thank you very much.
Thank you very much, Dr. O'Modhrain. That was absolutely fascinating and very interesting. I hope we do get a number of questions for you in the panel session. I'll be handing things over quickly to Dr. O'Malley while I set up our next session.
Sure. So Sheila, maybe we do have time for a question that's in the Q&A. Allison Okamura was commenting on your study looking at the role of proprioception in Braille reading. And she raises the question, and maybe we can revisit this in the panel, does integrating motion with tactile perception, is that important for interpreting the tactile feedback in the context of movement, or is it an issue of active exploration enabling more useful tactile feedback?
Ooh, it's certainly the second one. And I think in the case of tactile diagrams, it might also be true in the first. So if you think of like exploratory procedures like contour following, that's certainly about integrating movement over time. I think in the case of Braille reading, it's probably just that the amount of information that can be picked up is increased when there's an active slip between the finger and the surface, because you're continually stimulating the haptic receptors in the fingertip. I'm sure Lynette probably could add to that too.
Lynette, you're welcome to, if I see you there.
More or less Sheila's answers. I was screaming, sorry. No, I don't think I have anything to add.
Okay. So there is a small follow-up question from Munya regarding this work related to proprioception versus non-proprioception for Braille cells. If you've published that work, it'd be interesting to be able to share that.
Yes, that's in Transactions on Haptics from 2015. It's I can see if I can, while everything else is going on, I'll see if I can find the reference for you and pop it into the chat once.
Great. Thanks so much, Sheila. And we'll make sure to get that to the attendees as well.
Yeah.
So I think this gives us a great chance to thank Sheila for her talk and transition to the next talk in the schedule. So I'm going to pass back to Zane to take over for that.
Thank you, Dr. O'Malley. I'd like to encourage all the attendees to continue putting in their questions in the Q&A. Just make sure you indicate who it is for.